Compared to other countries, New Zealand now generates a larger percentage of its power from the wind, but dealing with its random nature can be a tricky business. So how do we learn to rely on the weather? Well, you turn to a mathematician, of course, like Golbon Zakeri from the University of Auckland. Hi Golbon, thanks for talking to us today.
Hi John.
So why is the randomness of wind such a problem when you're trying to provide a power supply?
Well, one thing that you would want in your power supply, probably the most essential thing that you would like in your power supply, is reliability. When you put the light on, if you're using your hairdryer or if you're using your computer, you want to be able to count on it running for a significant period of time while you're using it. So if your source of generation is intermittent and there is no backup for it, well, then you lose that reliability. That's why it's extremely important that if you are turning to a source like wind, which has a lot of advantages to it, that you make arrangements to cover the disadvantages, such as intermittency of wind, so that then you're faced with a reliable power supply.
So what sort of periods of time are we looking at in terms of reliability?
Okay, that's a really good question. So wind is of course intermittent in various time intervals. It's intermittent in 5-minute time periods. It's also intermittent over longer ranges in a matter of few hours, and also if you're banking on wind for a significant portion of your generation, it is possible to have several days where you basically don't get any wind, as one might have experienced in New Zealand. And all of those time intervals, they present their various challenges, and they need to be sort of looked at, foreseen, and backed up. So for the 5-minute time interval, when the wind changes its direction or when it just all of a sudden falls, what you need to do is you need to ensure that the system has enough frequency to maintain the 50 hertz that we have in New Zealand, and it doesn't all of a sudden drop and cause a blackout, a rolling blackout. For longer terms, you need to basically cater dispatching other mechanisms, so use either hydropower, which we have quite a lot of in New Zealand, or thermal generation, in order to ensure that there aren't days where we would have to actually schedule, for instance, cutting off of power supply, or you need to utilize demand response. So for each of those, as I said before, for each of those sort of sets of time intervals, there are different kinds of solutions that one would have to work with and have to be sort of clever about. So this is where the optimization comes in.
I see, because you've got a menu of different power sources, plus this time variable to throw in.
Yes.
So clearly you've got to come up with, this is where the mathematician comes in.
Exactly.
There's an equation that will
Yes.
sort it all out. So what sort of maths do you use to try and work this out?
So just as you pointed out, there are several elements that comes into this problem. One of them is the randomness, the random or intermittent nature of wind. The other one is the fact that we have multiple kinds of power supply. And then the last thing is the intertemporal, sort of the time element of this. So the best tool that we've been able to think about and come up with is using what's called stochastic optimization. So like other kinds of optimization, what you're intending to do is do the best that you can, the most cost-effective and environmentally friendly approach to generating electricity over various time periods with the power sources that are at your disposal. So this is the scheduling, the optimal scheduling of generation of power. However, you need to take into account the intermittent nature, which is the stochastic part. So faced with an uncertain future, so we don't know what the volume or the direction of wind is going to be, what is the best way that we can decide on scheduling power generation right now, of course, without having had the hindsight.
Mm-hmm.
So there are a number of models that are available for these kinds of problems. When you go to the literature, you look at stochastic linear programs or stochastic nonlinear programs. They take into account various different periods of time, so they could be multi-stage or they could be two-stage stochastic optimization problems. And really, we're sort of, this approach is very much in its infancy. It's kind of the leading edge. We've just started with two-stage stochastic programs for scheduling wind supply. And we're working out to see whether it's a good and reliable way of doing this, and it's shown quite a bit of promise.
Stochastic optimization.
Yeah.
So what does that really mean? Is just stochastic optimization, is that just another word for random?
What it means is, as I said, with the optimization part, you're trying to do the best,
yes,
right, given a set of constraints. So ordinary optimization has applications to things like scheduling how your crew fly an airplane. Okay, this is something that a lot of work is done in Oakland in. Or how you schedule getting certain sets of jobs done on particular machines. Okay, so the optimization part of electricity generation comes into scheduling the various power plants, but the stochasticity is in the uncertainty. So really, it's making the optimal decision under uncertainty, doing the best that you can do, given that the future is uncertain.
So is that a calculation that would go on in real time all the time?
Absolutely.
As things change?
Absolutely, absolutely, that's the case, yeah. So this is why many stochastic optimization problems are multi-stage stochastic programs. So there are various time epochs that are involved, and you do some kind of planning and possibly revisit the problem and give it a dynamic nature and do another best that you can for that period of time, given that your future is uncertain, and then do it over and over and over again.
So from your point of view, do you actually work and communicate with someone like TransPower?
We do, yes, we do quite a bit of work with TransPower. TransPower, we're actually keen on sort of adapting their current model, which is a deterministic model, into a stochastic framework that would allow for wind intermittency. However, the two-stage stochastic program is quite large if you allow for all the various possible scenarios that might eventuate with respect to wind. So right now, this is a kind of a pilot project. It's not something that TransPower is using or is going to use. Okay, so they have shown interest in looking at the stochastic version of this. They do have some other work that they have to do prior to transitioning to actually taking this probably more seriously on board. There is also intermittency and stochasticity that comes from other sources as well. You might have line failures, or the capacity of the line, depending on weather, may be different. Okay, and that would have an impact on how you're going to schedule your power generation sources as well. If you are relying on generating a whole lot of electricity from the South Island to get it up to the North Island for use, and the high voltage DC cable that goes underneath the Cook Strait has reduced capacity for a particular period, then you would have to do some rescheduling. So TransPower have very recently shown particular interest in perhaps attacking that problem. So it is something that's in their mind. Whether or not anything sort of tangible will happen in a short time period, I'm not really sure.
Is it something that could also be used for solar power?
Yes.
Is that another kind of
yes.
random
Yes, absolutely, absolutely. Yes. It could be used for solar power or other sources of generation that are intermittent. So we also have sort of intermittency or uncertainty actually in our hydro resources. We don't know when our hydro lakes are going to be full. We don't know what the rainfall is going to be. It's over a different kind of time period. And the aspect that hydro has that wind doesn't have is that you can store a whole lot of water in the lakes, whereas you can't store the wind. So if you're banking on generating from wind, it has to be there.
Yes, I was going to ask you about that because I was thinking, I guess the only way you do that is having massive batteries or something that stored this wind power.
Yes, massive batteries is one thing. Another thing that people are talking quite a lot about are actually electric vehicles. So what you can do is that a large collection of electric vehicles can act possibly as a battery. So you could charge them up when the wind is blowing, people could use them, and then in the event that the wind falls, you could request that these vehicles now be a source of supply into the power grid. So that's one possibility. Another possibility is what's called firming wind. So what that means is you have another source of generation, power generation, such as hydro, okay, that if you think about it, you couple this with wind, okay, and when the wind is blowing, you use the wind, and when the wind is not blowing, then you use the hydro. Now, when the wind is blowing, you could collect the rain in your hydro reservoir, and that effectively is we would act as a bit of a battery.
Well, it's a bit like hybrid cars, isn't it?
Yeah,
You know?
absolutely, absolutely. But the stochastic optimization approach allows for all of these bits and pieces to be integrated in one big pot, rather than individually carving things out and saying, okay, here is a wind farm, and now we're going to couple it with this particular hydro lake, okay, and offset the risk, so to speak. We would say, well, here are all the available resources, here are all the volatilities that are involved. What's the best approach to this? The most cost-effective approach?
Well, it sounds like a pretty complicated kind of equation. Do you enjoy working on these sorts of models?
I enjoy working on these models very much for several reasons. The application is a very interesting application. It's one that we all rely on, electricity. It's nice and relatively easy to describe, but also the mathematics that comes from it is powerful and intriguing. And on top of this, there is, I guess, another layer, which is participation in the electricity market by the various generators and consumers, and how each of them can kind of have their own say. So consumers can respond to electricity prices by cutting back the usage. Electricity generators can make the prices sort of more expensive by offering in more expensively when there's a drought or a perceived shortage of power supply. And that brings in an element of sort of economics and what's called game theory. It makes the whole package very interesting.
I see. So this is potentially more addictive than Sudoku, really, working on stochastic
absolutely.
mathematics.
Yes.
Has it got any application in your day-to-day life? I mean, does it help you predict when's a good day for a picnic with the family, that kind of thing?
That's a good question. I'll do some more simulations on that before I can report.
All right. Yeah. Well, thanks very much for talking to us today, Golbon. Really appreciate it.